know that these patterns even exist. And this approach of letting computers learn patterns from data rather than following hand-coded rules is what we call machine learning. So machine learning is a subset of AI, or in other words, just one way to achieve artificial intelligence by giving machines an ability to learn automatically and self-improve from experience without being explicitly programmed to follow some rules. And here is an interesting fact. In 1997, a chess-playing supercomputer developed by IBM called Deep Blue defeated Garry Kasparov in chess, a chess grandmaster at the time, and it was this breakthrough moment in AI that everybody was talking about. But interestingly, Deep Blue did not use machine learning. It used symbolic AI with brute force, search, and handcrafted or manually programmed evaluation functions, which means it did not learn from data or improve its chess skills through experience. All the strategies and evaluation criteria were programmed by human experts and chess grandmasters into Deep Blue. So for a long time, machine learning was not even considered the best and the most efficient way to create artificial intelligence. Instead, a lot of focus and work was actually done in symbolic AI field. Now, to understand the comparison between these two better, let me give you an analogy. Imagine you are teaching someone to bake cookies by giving them an explicit recipe with precise steps, like add 2 cups of flour, mix for 3 minutes, bake at 350 degrees for exactly 12 minutes. So this approach uses clear rules that must be followed exactly, step by step. So this approach of creating explicit rules and logic for a computer to follow, where everything is defined through logical rules, would be the symbolic AI. Now imagine instead of giving someone a recipe, you show them 100 samples of successful cookies and failed cookies. You don't tell them exact measurements or temperature or duration, but they observe patterns. When the dough looks this way, the cookies turn out well. When temperature is between, 347 and 351 degrees, the cookies turn out the best. So they learn from examples rather than following explicit rules. And this approach of having computers learn patterns from data kind of reverse engineer the rules from the data instead of following pre-programmed rules, and this would be machine learning. Now, this is very important to understand in the comparison of these two, and why the breakthrough of machine learning was much bigger than the breakthrough of symbolic AI. The biggest difference between these two was that machines could now learn patterns that humans never thought about. Let me explain. AlphaZero was a computer program developed by DeepMind that learned to play chess by playing against itself without human intervention. And what was remarkable is that it developed strategies that were completely different from traditional human chess theory. For example, it would make moves that looked bizarre to grandmasters, like sacrificing pieces with no immediate tactical advantage, but these moves would later prove to be brilliant long-term strategic decisions, because AlphaZero beat all the human chess players. And AlphaZero discovered these patterns entirely on its own through self-play, which was a moment that showed us how machine learning can find solutions that humans never programmed or even considered logically. So this was the first time that a machine went beyond the human logic or knowledge base. And before AlphaZero's breakthrough, symbolic AI was actually the dominant approach for decades in artificial intelligence. It was actually the primary paradigm between 50s and all the way through 90s. The symbolic approach was much more popular because it aligned with how we thought human reasoning worked, through explicit rules and logic. So most of the work was happening in this field. Computer scientists built expert systems with hard-coded hand-coded rules for everything from medical diagnosis to chess playing to everything that an intelligent machine was supposed to do. Now, machine learning existed as a concept in parallel, but only started to become a dominant approach after 2000s, with breakthroughs like AlexNet in 2012 and AlphaZero in 2017. And as I said, that changed everything because that breakthrough was revolutionary and completely different from the breakthrough of Deep Blue, because people saw that machine learning programs could suddenly discover patterns and strategies that were not explicitly programmed and might never have been discovered through traditional human reasoning. And as a result of that, started absolutely outperforming traditional symbolic systems in more and more domains. So that specific differentiator or that skill of machine learning algorithms actually made machines way more intelligent than any symbolic systems had ever been before. So starting from year 2000, we had a big shift from symbolic AI to machine learning. And that's where things got interesting as machine learning field developed more and more. So let's continue our story. Machine learning comes in different flavors. Have you heard all these weird terms like supervised learning, unsupervised learning, reinforcement learning, all these strange names that don't make any sense if you don't know what they are? So let's break them down simply so you understand clearly what they all mean. Let's say Netflix has data on hundreds of thousands of users who have already rated the show, so they can use this so-called label data to train their system. Now, let's stop here for a second. Label data, what does it mean exactly? Well, since we are on TechWay data, where we explain everything in detail, we don't skip things here, we're going to explain simply what label data means. Think about how you learned to recognize fruits as a child. Your parents showed you an apple and said, this is an apple. They showed you a banana and said, this is a banana. Or showed you a picture of an orange and told you, this is called an orange. Those names were the labels that helped you learn. They didn't just throw a bunch of fruits in front of you and say, just figure out what each one is called by yourself. So that's how we teach machines what a specific piece of data means by adding labels to them. In our Netflix example, label data works like this. When a user gives a show 5 stars, they're essentially telling Netflix's algorithm, this is something I like. When a user gives a show 1 star, they're saying this is something I don't like. These ratings are the labels. They're teaching the algorithm what good user review and bad user review looks like for the shows. So when Netflix wants to recommend shows to you, even if you haven't rated shows yourself, the algorithm can look at users who have similar viewing habits as you and what those similar users rated highly or poorly. Then it's going to assume people who watch what you watch tend to love this new show. So there's a high probability that you will like it too. Or it can think users with viewing patterns like yours typically hate this genre. So let's not recommend it. Without these star ratings as labels, Netflix would not know what you might enjoy or not. So instead of random guessing, using ratings as labels helps algorithm make educated predictions by associating viewing behavior to actual user satisfaction. So now Netflix collects data points like user A watched 20 comedies last month, binged Korean dramas, never finishes horror movies, and rated this new show 5 stars. They gather thousands of these subtle patterns from millions of users with different viewing habits and their corresponding ratings. The machine learning system then identifies patterns, like users who watch comedies and Korean dramas but avoid horror tend to rate this show highly. Netflix does not explicitly program these rules. The algorithm discovers them by analyzing the labeled data. This approach of learning from labeled examples, this is called supervised learning, because we're supervising the algorithm by showing it the correct answers during training. The labels guide the learning process, helping the system understand which patterns lead to which outcomes. And this is why companies invest so much in collecting and maintaining high quality label data sets, because the quality and quantity of your label data often matters more than the sophistication of your algorithm. Because as the saying goes in machine learning, garbage in, garbage out. Even the most advanced machine learning algorithms cannot produce great results with bad training data. Now, what if Netflix wants to understand different types of viewers without using any ratings or labels? Let me explain. Imagine Netflix algorithm looking at all their user data, what people watch, when they watch, how much they watch, but without looking at any ratings. It's just curious. Are there natural groupings of viewers that we haven't noticed before? The algorithm might discover something interesting on its own. Like, hey, I've noticed there is a group of people who only watch content between 11 p.m. and 2 a.m., mostly watch 20 to 30 minutes at a time, and jump between different shows. We didn't tell the algorithm to look for this pattern, it found it by itself. This might reveal a viewing category Netflix hadn't even thought of. Let's call them insomnia viewers. Or it might find weekend binge watchers group who consume entire seasons in 2 days. Or background noise viewers who put on shows while doing other activities. The key difference here, nobody told the algorithm what groups to look for. There were no labels saying this person is a binge watcher or this person watches for background noise. The algorithm discovered these patterns entirely on its own by looking at the raw viewing data. So these are patterns that we could not have known even existed. So there's no way to have labels for patterns that we don't even know are out there. And this approach, where the algorithm finds patterns and structures without being given correct answers, this is called unsupervised learning. So machine is learning without any supervision or guidance of what each data means. We're saying, here's a bunch of data, go figure out if there are any interesting patterns worth paying attention to. It is like giving a child a box of toys and watching how they naturally sort them by color, by size, by type, without telling them how they should be organized. And the child may discover the categories by themselves, just like the algorithm discovers viewer segments on its own. Now, why is this important? Unsupervised learning gives us superpowers that supervised learning simply cannot, because it helps us discover things that we don't know that we don't know. In the real world, we often have situations where we don't even know what patterns exist in our data, or what questions to ask even. Unsupervised learning can expose entirely new categories or segments or anomalies we never thought to look for. Plus, it saves tremendous resources, because labeling data is an expensive and time-consuming process. Imagine having to manually rate millions of Netflix shows and manually take millions of images or show ratings. But in addition to that, unsupervised learning also works with raw, unlabeled data, which means that it's perfect for situations where labeled data is either scarce or it's impossible to get. Now let's talk about the third major type of machine learning, called reinforcement learning. And this is quite different from what we've discussed so far. Think about how you learned to ride a bike. Nobody gave you thousands of labeled examples of correct and incorrect bike riding. And nobody just let you figure out random patterns on your own. Instead, you tried something, you fell down, which was a negative feedback, you adjusted your approach, and eventually stayed upright, which was positive feedback. And that's essentially how reinforcement learning works, through trial and error with rewards and penalties. Now let's use a fun example. Imagine Netflix is creating a system that autonomously edits movie trailers to maximize viewer interest. The system starts by creating random trailers, some of them showing action scenes first, others revealing plot twists right away, trailers that are highlighting the main character, and so on. Each trailer then gets shown to users, and Netflix then tracks whether people watch the movie after seeing the trailer. When the users watch the movie after seeing a specific trailer style, the algorithm gets a reward. So it gets a positive feedback. When users ignore the movie, it gets a penalty, as a negative feedback. The system does not know beforehand which trailer style will work best, right? So it discovers this through experimentation and feedback. And over time, as it shows more and more trailers and then analyzes the effects of each trailer, this reinforcement learning system learns that, let's say, action movie fans respond better to trailers with explosions in the first 5 seconds, as an example. Or drama viewers engage more when character relationships are highlighted in the trailer. Then we have horror movie fans that click more when the trailer builds suspense without revealing the monster. The algorithm was not supervised with labeled examples saying this is a good trailer and this is a bad trailer. It figured out what works by trying different approaches and then measuring the results every time through reinforcement. And this approach is exactly how reinforcement learning works. The algorithm learns by interacting with an environment, in this case Netflix users, taking actions like showing different trailer styles and receiving feedback whether users watch the movie or not, and then adjusts the strategy and repeats the process. What makes reinforcement learning special is that it can optimize for long-term rewards, not just immediate feedback. Because maybe a mysterious trailer leads to fewer immediate clicks, but higher viewer satisfaction later, resulting in more completed movies and subscriptions or higher ratings. So a good reinforcement learning system can figure this out as well. And there are some really interesting real-world applications for reinforcement learning. For example, think of self-driving cars that are learning to navigate safely through countless road scenarios. For example, say when the car brakes too hard and passengers jolt forward, that's a negative feedback. When it drifts over a lane marking, that's another negative feedback. But when it maintains exactly 3 seconds of following distance on highways and executes turns that feel natural to passengers, it's positive feedback or reward. And this feedback helps the car learn the ideal driving behavior. So every action it takes results back into feedback like gaining points or losing points, just like in a video game. And the car learns that was a good behavior, that was a bad behavior, and it adjusts accordingly. And over time, it learns what good is and what bad is. Or think about robots learning to walk or manipulate objects. Again, they do something, they get immediate feedback when they drop an object or fall over, so that they can adjust their movement through lots of trial and error. Game-playing AIs are actually another example of reinforcement learning, like the ones that master chess, because they receive very clear rewards for winning and penalties for losing. And this actually helps them discover strategies by learning what chain of moves lead to winning and what leads to penalties. And that's exactly what helped them discover strategies that humans never even thought of. So in each case, the system improves through experience rather than explicit teaching or unsupervised pattern finding. So we have explored the 3 main approaches machines use to learn from data. Now, you might be wondering, how do these AI breakthroughs actually impact engineers like us in our daily work? Well, that's that's where today's sponsor, Work, comes in. Work is a leading AI coding agent which was built for the entire software lifecycle. Work actually features a state-of-the-art coding agent, built-in code editor, and an intelligent terminal all in one environment. It has the powers of, and now let's continue with the video. So supervised learning, unsupervised learning, and reinforcement learning are different ways of how machine learning systems learn from data. And to make these concepts click even better, let's see an analogy of how these three actually all compare to each other. So supervised learning is like learning to bake cookies without a detailed recipe, but with many examples of both perfect and failed cookies to examine. So you're given ingredients, which is the input data, and actual finished cookies, which are the labeled examples, where in each cookie you can observe their golden brown color, feel the perfect chewy centers with crispy edges, maybe smell the vanilla butter balance and taste the sweetness. And on the other side, you may have burnt, rock hard, failed cookies or undercooked ones which are too soft. So you basically know which ones are good and which ones are bad examples. And without being told exact temperatures or timing or techniques for baking these cookies, you must now study the patterns across hundreds of examples until you recognize which combination of ingredients, heat, time, and so on consistently produce that ideal cookie. Learning entirely from these examples rather than following explicit rules or recipe, just as supervised learning algorithms discover patterns from pre-labeled training data. So the goal here is to figure out the best recipe to baking perfect cookies better than any existing recipe. Now, unsupervised learning is like being given a refrigerator full of ingredients, but no guidance whatsoever. Nobody tells you what dishes to make or how the ingredients should be combined. Nobody gives you a sample data of this is well made, this is badly made. You have to figure out everything from scratch. So you start cooking from all these ingredients and you start noticing natural patterns. Like these ingredients share similar textures, and these ones create comparable colors, and these ones create this type of colors when combined. You might group ingredients into categories, which is called clustering, or even identify unusual combinations, which is anomaly detection. And as a result, you may discover entirely new recipes that no human has tried before, but taste amazing. As an example, maybe finding that cardamom enhances chocolate in a way that traditional recipes never considered. So the goal here is to discover new taste combinations, dishes that don't yet exist. And the reinforcement learning is like being a chef who wants to maximize the customer satisfaction for her restaurant. So you start experimenting in your kitchen, trying different combinations of ingredients and cooking techniques, similar to being given a refrigerator with all the ingredients and you're just basically trying to figure out what new dishes to make. But with a difference here, which is every time you prepare a dish, you go out and get feedback from your customers. They rate the taste, presentation, the texture, the originality maybe, and so on. The main part here is that you get feedback and you adjust based on that feedback. But in the customer feedback, it's important to note that nobody tells you exactly what to change. No one says, add more salt here, or cook it 2 minutes less, because your customers don't know what you need to add or adjust. They just know whether they like it or not. So you only see the feedback scores of your customers, how they rate your dishes, and those scores are either going up. So we've explored supervised, unsupervised, and reinforcement learning, which are the three main approaches machines use to learn from data. But you might be wondering, what's actually happening under the hood? Like, how does a computer process all this information and make these intelligent decisions? Where's the mechanism that powers all this? Well, we had traditional or classical machine learning algorithms. with some confusing names like linear regression or decision trees that actually showed some impressive results, but still had very limited learning capabilities because they were all designed to follow strict recipes with clear instructions. For example, for our Netflix use case, a linear regression model might look at factors like how many action movies you've watched and how many Tom Cruise films you rated highly in order to calculate a simple score for recommending Mission Impossible. But it would struggle to understand